Hello everyone and welcome to the new lecture of motion control systems. I hope all of you are in good condition along with your beloved ones and all of you are preserving your health. If you remember, last week we started the discussion on motion control systems with multiple components, and we actually made a derivation on an example study about grasping control algorithm. This week we'll continue with the same topic, and we will be covering a very interesting application of motion control systems with multiple components. Let me arrange my pen. Well, today I'm going to cover with you the bilateral control systems. Let me write it here. Bilateral control systems. Of course, when we say bilateral control systems, we are actually referring to systems that might potentially include certain delays. That's why I have to highlight here that the one that we're going to cover will be without time delay. Alright, so let's start with the first half of the lecture will be more like a discussion and conceptual introduction to the field. I'll try to describe you in detail what's bilateral control, what kind of properties do we expect from a bilateral control system, and what are the applications of bilateral control systems, and then I will be moving towards the derivation in the second half of the lecture. So, we have a good question in hand. What is bilateral control systems? Sorry, I have to arrange the color. Question. What is bilateral control systems? In other words, why do we have and the notion of bilateral control? What's it? Well, there are many different ways to describe that thing, but I'll try to do it with my own words since this is also in my research field. Bilateral control is let me put out an answer here. It is coupled control of forces and positions to provide the transmission of haptic sense. So you may ask here, what's haptic? What does this word refer to? Let me also give an explanation for this. Let me put here. Haptic means the sense of touch. Alright, so I'm having a small look at my notes here. Okay. Bilateral control systems are sometimes also called telemanipulation or teleoperation systems. Let me write here that they're also called as telemanipulation or teleoperation systems. The meanings of these two words, teleoperation or telemanipulation, will become obvious in a couple of seconds. Now, I'd like to express what bilateral control system stands for in an illustrative example in the next slide. So, for bilateral control system, we need at least two systems. Most of the time, we take these two systems to be identical, but there is not such a requirement. I mean, these two systems can not necessarily be identical or sometimes be different in configuration or dimension. So let's take a robot here. Let's take a 2 degrees of freedom manipulator here. And let me also take another one somewhere here. Okay. So let's put the secondary manipulator here. Well, I'm sorry for my bad drawing. Okay, I think this is better. All right. So, traditionally, we will be calling these two systems as the master system, or we may call it master robot. We will call that system also the slave system, or in another setting we might call this also slave robot. So these two systems are physically separated from one another. What happens is that a human operator comes and applies certain force on the master system. Let me write that this is simply human operator. A human operator applies certain force on the master system and slave system moves. Well, as it goes through its trajectory enforced by the human operator, of course, after a while it will be interacting with an environment. Let me try to draw it better. So we will have an environment here that's called the remote environment, or just simply the environment. Let me put it here, the remote environment. So, of course, if we're talking about a physical medium, we should have certain damping and certain stiffness for this medium. So, human operator applies certain force on the master system, and the slave system is supposed to follow the position reference enforced by the human operator in the remote side, and is supposed to feedback whatever interaction force exists on the remote side to the human operator. So the task can be represented by this figure. You have X master, and you have here similarly X slave, and here we're gonna have F master, the force that the system exerts back to the master operator, and here we should have F slave. Let me also put this side. So X slave, F slave. So what we want is that, let me take a different color. So this is one side, that's the master side of the problem, and this part is called the slave side of the problem. Sorry, I'm still trying to learn how to write with this pen. Okay, so these two sides are geographically separated. This and this side are geographically separated, and there is no physical connection between those two sides. No physical connection. So what happens is that through only signal transmission, a controller sitting somewhere here tries to exchange signals with the master and the slave system to provide these these two tracking objectives. Well, that is the actual case. And let me also go to the next slide to draw you the ideal case. Well, ideally what we have is this. So this is human operator. Let me also put somewhere here the slave environment. Okay. This is the slave environment. Slave environment with the proper damping and stiffness, of course. Now, in ideal case, we want a system that will behave like a virtual massless stick between the slave environment and human operator. Okay, this is virtual massless rod connection between the master and the slave sides. So let me put here virtual massless rod connection with infinite stiffness. When we say infinite stiffness, what we want is that, in the ideal scenario, as human operator gives certain motion, the slave environment would be, the slave system would be mimicking or copying the same motion without any divergence from the reference, and whatever interaction force exists here between the environment and the slave system and the tip of the slave robot should be directly fed back to this side, which means that this rod should be massless and behave with infinite stiffness. So that is an idealization of this scenario. Well, So we have here, actually, maybe we can. Okay, this is ideal operation. Okay, once more, let's go back to the previous slide. In actual scenario, we have separated systems and a centralized controller transmitting signals. These are the signals from the sensors of the master and slave system, actually, transmitting signals between those two systems so that it provides us with the ability to touch a remote environment. I mean, the controller. So if we want to idealize this scenario, it is as if we have a virtual stick between the human operator and slave environment in such a way that this stick does not have any mass, so it doesn't have any force contribution, so, from the stick, from the rod, and the stiffness is infinite. So the motion carried out on the human operator side is directly mapped to slave environment without any distortion. That is the actual and ideal operations. Well, if we're talking about operation, what kind of metrics, okay, let me write here, performance metrics of a bilateral control system. Well, how can we evaluate the performance of a control system? So, if you're talking about a control system, above everything, what we want in the first priority is to have a stable system. In other words, the first requirement we're expecting from our system would be stable operation. So no one wants oscillatory behavior or unstable behavior from a system that is supposed to act in a remote location. So that's called stability criteria. Let me write here stability criteria of bilateral control systems. Second is that's very specific to the bilateral control systems, because the first one is the primary requirement from any control system, not necessarily only for bilateral control, from any force control system, from any position control system, from any other kind of control system, no matter if it's a robot, if it's a drone, or if it's an autonomous vehicle. We first require stable operation. That's required. And second is specific to teleoperation systems, transparent operation. So that is pretty new notion for us. What is transparency? Let me write here transparency. I didn't make any definition for the stability because you know what it means. We're actually talking about BIBO stability, bounded input, bounded output stability here. But for transparency, I have to give a definition. Let me write in the broadest sense. It's actually a measure which shows the ability of the controller to transfer operator motion and environment forces. Let me write to transfer operator motion and environment forces. Okay, well, let me try to state this with a little bit different wording. The transparency is pretty specific to teleoperation systems. You can also call it bilateral control systems, the telemanipulation systems. I'll be interchangeably moving between these words. It's very specific to teleoperation systems, and it's a metric that shows how well the operation is performed. So in order to understand this, you have to look at the master side input position, slave side output position. Are they matching one to one? And the slave side interaction force and master side interaction force, are they one to one with different signs? Because you're giving your input from this side, and the slave side is supposed to go to the other side. So forces are actually with different signs, but they have to be of equal magnitude. And transparency is the measure of how much matching exists between the forces and the position responses of the master and slave systems. Well, further about the details on teleoperation systems. Well, let me write here applications. Well, actually, let me see. Before the applications, I would like to first state the historical side of the issue. So, historically, now, bilateral control systems, or as also referred as the teleoperation systems, have been studied since the beginning of the first electronic devices that can control manipulators. So that more or less corresponds to the time of 1940s, 1950s, or maybe early 60s. So starting from these years, many people worked on very different applications of teleoperation systems, telemanipulation systems, and historically they have been dealing with different aspects of the teleoperation problem. But when I say historical background, I would like to also talk about two different issues. Well, let's start with the development of the technology, and let me go back to the beginning of the 1900s, or to the end of the 1800s. So we first had the transmission of sound, the phonetic signal, I can call it. Transmission of sound. What's this? That's actually what we are always doing when we are having some phone calls to somewhere, right? So, starting with Alexander Graham Bell, people came to the point where they could be able to transfer their sound to distant locations, instant transfer of sound to distant locations. So there is a specific there's a specific word for this. We call that device the telephone. This tele word in Latin means over a distance. So telephone refers to the device that transmits your phonetic signal, your sound signal, over a distance, so to a distant location. And that was the first improvement in the transmission of sensing of, or let me say, in the transmission of one of the human senses. So if you move through the history, the second one was transmission of image, or I can call it visual information. For this, after the telephone, we then invented the device television. That's the device that transfers the visual information over a distance. So with these two, we were able to transfer the hearing ability of or speaking ability of mankind to a distant location, and to transfer the visualization ability of or visualization sense of human being to a distant location. Now, if you move through these two, it's easy to come up with the idea that what happens if we try to transmit the sense of touch. So we have the sense of hearing, we have the sense of uh, visualization, sense of seeing, let me say, and we want to also transfer the sense of touch to a remote location. And the systems for this are called tele manipulation or tele operation systems. So that's manipulation over a distance, operation over a distance, like the telephone and television. But there is a slight difference between the first two and the last one. What happens here in the telephone? There is a microphone here. You speak to the microphone, sound signal comes, and this is converted to some electrical signals being transmitted to the remote site, and through a speaker here it's being reconstructed. So you talk, the device senses your voice, transmits, and another device creates that voice on the other side. If you follow the signal path, this is unilateral. So that's called one directional, right? You're talking as what I'm doing right now. I'm talking to the microphone, it takes my signal, and when you're playing it back, it transmits back to you through the speaker uh, of your computer. Transmission of image is a similar scenario. So you have some action here, you're recording your action through a camera, and this signal is being transferred to electrical signal, and on a screen you are creating the same image, right? So that is also unilateral. Okay, so the guy can make any motion there, the camera records it and sends it back, and the guy on the other side who is watching the television can only see it but cannot give visual feedback to the other side, to the original person. But transmission of the sense of touch is different. This is where you are actually interacting with a robotic system. Let me put it as the master robot. And the signal is transferred to electrical medium, and on the slave system, slave robot, you have interaction with the environment. Okay, that's the interaction with the environment. But let's have a look at this structure. In this system, different than the transmission of image and different than the transmission of the sound, in the transmission of the sense of touch, you first have to give certain action here, right? And this action is replicated on the slave side. A reaction is generated, and this reaction is reconstructed here. So you give the action, this replicates, but throughout the operation, throughout the manipulation, you come up with certain forces between the slave robot and the slave environment. And these forces are also fed back to the human operator so that you can feel the sense of touch. Otherwise, it will just be giving input, position input, and the other system will make any motion without any force feedback. And without the force feedback, you cannot call it the sense of touch. So this makes a different system, unlike that one and that one. Unlike the transmission of sound and image, here in transmission of sense of touch, you have bilateral action. So it's two ways, twofold action. That's why we also call those systems bilateral control systems. I hope actually the word bilateral is now obvious. Okay, I can tell that there are now very good solutions on transmission of sound. That's industrialized. You have the cell phones everywhere. There are very good solutions on transmission of image, the broadcasting systems, the internet medium, the televisions. They're now very operating in a very stable and clear manner. They're of high quality, but the sense of touch is just kind of out of research and slowly starting to become industrialized. So in a few years, you'll probably see devices around that provides you with the ability of sense of touch as if you have the cameras and the televisions today, or the sound capturing systems and telephones around. So I can also claim that this is, I mean, the research phase is mostly completed in the transmission of sense of touch, even though there is still research going on there, like the research still going on in this transmission of sound and image systems. There is also research there, but certain industrial outputs are now available, and in a couple of years you'll see their products. Well, talking about transmission of sound, transmission of image, and transmission of sense of touch, I would like to also highlight another point that is a very active research field. So once people started to have the ability of transmit the sound, then they came up with the idea, they came up with the idea to record sound. So recording and replay of sound information. Any kind of audio recorder today is doing that. You're giving your sound signal, it's being recorded. And second is recording and replay of vision. So television was used for the remote transfer of the visual information, and recording and replay is a little bit different. Historically we had first the cameras using mechanical equipment, and nowadays we have at every corner those devices, either the cell phones or specific digital cameras that are capturing images and recording on a digital environment like an SSD card. So these two are again unilateral operations, having the ability to record and replay the sense of touch is a little bit more tricky, because this was unilateral, and that last one is bilateral operation. So you need a bilateral operation or bilateral control system to record and replay the sense of touch. You might ask, Well, what's the notion of replay of sense of touch? Why do we ever need a, such a system actually? It's very easy to understand. Think a little bit deeper. Think of a surgeon who's making a complicated surgery on your body. Would you prefer a very well a good surgeon that's highly experienced in his field to come and operate the surgery on your body, or you'll simply prefer you know a very young doctor who doesn't have that much experience? I'm sure that most of you would prefer the well experienced doctor. And what's the difference between the experienced doctor and the doctor who's not that much experienced? It's very simple. The experienced doctor has, throughout throughout his career, has encountered with a lot of different cases, different scenarios, and knows where to approach, how to cut your tissue, how to make the stitching, or how to carry out the operation over there physically. But for an apprentice doctor, let me say, for an intern doctor or for a doctor newly graduated, there's no that much experience, and unless he gains enough experience, he will not be as talented as the experienced doctor. So you can use such a system, recording and replay of sense of touch system, uh, for educating people who has to deal with interaction and force feedback systems like the surgery. Or another example would be trying to teach your children how to write, because writing is also an operation that requires precision control of position and force together. And for this, you can record your own handwriting, the sense of touch through your handwriting, and replay it in another system to teach your children how to write. So, I think I've talked too much about the history. Let me move towards the applications of bilateral control systems. As I was stating, this class will be reserved for the background info, and in the next lecture set, in the next lecture video, I'll be making for you the derivation. Let me write here, applications. What are the applications of bilateral control systems? Well, let's think together. Here there's a master system where a human operator can operate, and there is a slave system in a remote location that's geographically separated without any physical connection except the signal transmission. And actually nowadays you can even make the signal transmission in a wireless way without using cables. So what can you use this system, for what can you use this system? The first thing that comes into my mind is handling dangerous materials. Let me write here, operation in dangerous medium. Here we may call it nuclear, we may call it chemical, or even biological. These are just examples. Okay. Well, think of the Chernobyl event. If you had teleoperated robots there to be controlled, you would save actually many lives of those soldiers who were trying to compensate, pour some concrete on the molten power plant there. Think of a chemical leakage in a production plant in order to check in order to make some measurements, in order to uh, carry out certain operation in the dangerous zone. Rather than going there yourself, you can send the robot and teleoperate it or control it from the remote site. These are good operations, and actually that biological is important. Until recently, people were not thinking of that biological side too much. But now we're in an epidemic, and think of a patient who has coronavirus. He has to be taken to quarantine, so he has to be in an isolated environment. And in order to save the life of the nurse or the doctor who is dealing with or who is helping to that guy, you can actually use a teleoperated robot, for example, to carry out his food, to, let me say, to manipulate the or to take some measurements from the patient, or even to insert some medical care to his blood cells, to his blood. So you can use a teleoperation robot for dangerous operations that are risky for human intervention. Let me write the other one. I'll write here telesurgery. Well, those Da Vinci control systems, Da Vinci robots, are nowadays very popular for medical robotic surgery systems. They're actually easy to use for doctors, and they ease the lives of both the doctors and the patients, because rather than opening a big wound on your body with very small tiny spot that just requires one or two stitches, you can enter the body of the guy and you can use that surgical robot to carry out operation there. But for this, you still need to be in the same room with the teleoperation device. I mean, as the doctor, you have to be in the same room with the teleoperation device. You cannot carry out in a remote site. So if this can be extended further, a doctor sitting in his master system chamber or room in Ankara, for example, can operate another doctor, another patient in Istanbul. Or you can even move to international area. A doctor in London can operate a patient in New York. So telesurgery will be possible once the applications are widespread, once the teleoperation applications are furthermore widespread. I can write here remote vehicle operation. Well, that's more or less similar to what we wrote in the first item, operation in a dangerous medium, but let's think about it a little bit more. Remote vehicle operation. If you have a construction machine, for example, that is supposed to work in a very dangerous area, like a flood, if there's a flood, there is water everywhere, and it's even risky or dangerous for the operator to sit inside that construction machine. If you have a teleoperated system where you can get the force feedbacks and where you can command out the inputs, remote vehicle operation can be easily handled without creating any danger to the operator himself. Well, I can write here another item. Space robotics. Space robots. It's very costly to train an astronaut here on the Earth and send him up there to fix some part of the space station or to carry out some operation there. If you have a steady robot up there in the space, very close to the station, that can be operated remotely from the world, this is gonna cost much less than training an astronaut, and this is gonna be much less risky in terms of human life. Well, I can write here another item. Micro nano manipulation. So, if you have a teleoperation system, by proper scaling, you can scale your motion down in such a way that you make some macro motion, and you make some macro motion on the master side, and the slave system scales it down and carries out certain micro motion. So this can be easily used for systems that are supposed to interact with micro objects. So this can be used in MEMS technologies. This can be used in biology if you want to inject some material inside a cell, for example. So you can use teleoperation systems there, and there are examples in the literature that people are using also teleoperation for this. And maybe I can write here some more fantastic output of teleoperation systems. This is new generation entertainments. Well, I was always claiming that, if you have a teleoperation system, one day it might be possible to play tennis in a virtual environment with someone in another country. So you have the master device here, you're holding the stick there, you're trying to apply certain force, and based on your applied force and the force feedback of the virtual model there, you shoot the ball there, and the same is being handled in a remote environment, so you can play even tennis with another guy in a distant location one day. I don't think that there's too much for this. In a couple of years we're going to have such systems around. So I think for this lecture I can also introduce the definition of the problems, and then we can stop there to start the controller derivation in the next lecture. So let me write here problem definitions. Well, I can use better word for this actually. Existing problems of teleoperation systems. When I say existing problems, I'm actually referring to the problems that are being well studied but not fully solved in the literature. Let me write here first. Classical problem definition. The teleoperation problem can be stated this way: x master minus x slave is equal to 0, and f master plus f slave is equal to 0. So the meaning of those two equations are, from the first equation we can understand the first objective. Master position and slave position differences should be equal to 0. This means that whatever position reference is enforced on the master system should be one-to-one copied or replicated in the slave side without any errors. So that's the problem definition. I mean, in the ideal scenario, we would like to achieve this. For the force responses, it's a little bit different, because since the force being applied to the master side is showing one direction, whereas the force on the slave side is from the other direction, we will have change of signs of force. It's like this: force from here and force from there. So because of this change of sign, the master side force plus the slave side force should be equal to 0. That means that the slave side force should be equal in magnitude to the master side force with changing sign, with an alternative sign. Well, that's the classical definition of the problem. But of course, if you try to go deeper into the research side of the problem, research side of the teleoperation systems, well, let me write active research topics. I can write here time delay problem. Time delay problem. And well, before moving to the next one, let me explain this time delay problem. Time delay exists in motion control systems if there is transmission delays, if there is delay in the perceived signal or the transmission of the input signal. And if we're talking about systems that's geographically separated, like a system sitting in Turkey and another one in Japan, of course there will be certain amount of time delay throughout or on the signal transmission between the remote site and the site here. So time delay is a serious problem, and people have been, I mean, scientists have been working on this problem for many years, and they have actually, I also worked on that problem for a while, and we have actually come up with certain solutions, but those solutions still require certain improvements. Time delay is still an active research topic in that field. I can write here as the second research-wise problem, the scaling problem. Thinking of two of those examples that I have given in the previous slide. One is remote vehicle operation, the other is micro-nano manipulation. So for remote vehicle operation, you might need to understand the forces that's in the scale of hundreds of kilograms, but if you try to use a system with hundreds of kilograms on the master side, I mean that gives forces equal to the hundreds of kilograms, you will not have safety there. So, in order to provide this operation, in order to have this operation, you have to have on the master side small scale and on the slave side big scale, right? So it's like I would like to feel the force as if it's 10 newtons here, but on the other side in the remote environment, the excavator applies 1000 newtons. It's like 1 to 100 scales. And similarly for micro nano manipulation, it's like this. I would like to make, for example, injection on a cell, but the cell itself has diameter of 200 micrometers. And for me, with my hands, to understand what's 200 micrometers is very difficult because we are in the macro scale in comparison to that one. So there, teleoperation systems with the master side operating as the macro part and the slave side operating as the micro part would be required. So in order to provide this, you need to have certain scaling between the master and slave systems. And maybe one of the last problems here is changing degrees of freedom problem or configuration problem. Let me also capitalize this. Okay, what's changing degrees of freedom or configuration problem? There might be scenarios or cases where the master system being operated by the human operator has different linkage, mechanical linkage, has different geometry than the systems acting on the slave side. So these two systems, master and the slave system, are, even though usually taken to be equal, identical systems, there might be some operations where they are different. And when they are different, they'll have internal disturbances acting one another, like series robot on one side and another parallel robot on the other side. Like let's take the master robot to be parallel and the slave robot is series robot. The force feedbacks will be totally different. Internal dynamics will be totally different. Frictions will be different. Gravity effects will be different. So the compensation of those differences is also another problem, because eventually what you want is to map the forces and positions one to one. That one here, this x master minus x slave and f master plus f slave, is the fundamental goal for any teleoperation system, even if the degrees of freedom is changing or the configuration between the master and slave robots are changing. Well, I think it's time to stop here this lecture, and I'll continue in the next lecture with the derivation of bilateral control systems. Before I close, actually, I want to make announcement, or let me preserve my announcement for the other lecture. Okay, take care.